Hello everyone, welcome to the next part of this lecture. Again, in the previous part, we started with what is Laplace transform, right? Which is essentially a frequency domain conversion of a time domain signal, and the Laplace domain is a kind of an S domain. And we kind of looked at the function on how to do it. We looked at the unilateral versus bilateral as well, and how in circuit analysis we are only interested in the unilateral Laplace transform. We started looking at the switching behavior, and we say that we can potentially model it as a step and impulse functions. So we started talking about the step function, and we are going to continue that step function in this part of the lecture, and the next part we're going to start with impulse function. Practically, we were looking at this discontinuities, right? And the analogy of that discontinuity is these switching operations in our RC/RL circuits, and that creates abrupt changes. So we were seeing that how they can potentially be modeled as a step function. So for example, the step function that we looked at, the values went from 0 to k in approximately at the instant, right? But when we were to mathematically model it, we assumed that okay, in between 0 negative and 0 positive, we can assume a linear approximation, that it is going from the value 0 at 0 negative all the way to 0 positive to the value k. Then the value at 0 is going to come out to be zero point 0.5 times k. So we kind of define the step function like this while modeling the discontinuity as a linear approximation. So we're going to kind of continue with the step function in this part of the lecture and learn more about it. Okay, so let's continue. By the way, another important point that we want to mention is we know that in most of the again in the first chapter that we talked about, where we had RC and RL circuits, and we were talking about the switching operations, and in most of the cases we said that the switching operation happened t is equal to 0. But then where we had multiple switches and we were switching one switch before the other, right? We also said that the second switch is happening after some time, right? So it has some positive time after time t is equal to 0. So potentially this discontinuities, again, switching, if switching represent a discontinuity, discontinuities can happen in our circuit analysis other than other positive t times which are not t is equal to 0, right? So for example, again, sequential switching that we also discussed as an example previously. So we're going to define another variable a where the switching can happen, right? So for example, the step, a switching operation can occur at t is equal to a. If the switching operation will occur at t is equal to a, right, your essentially your step function will move all the way over there, right? So previously, right, so previously if your step function was happening exactly at t is equal to 0, right, now your step function will start at a, and then it's going to move over here, right? So it will be time shifted. Whenever the switching operation is happening, of course your switching action is going to happen after that, right? At that point. So we can model that function as k times, again, k is amplitude of the function u of t minus a. And again, the switching operation, think of as a kind of a very practical circuit analogy, is the switching operation, right? That before that time of the switching a, the value was 0, and right after a, the value will be k, right? So for all the values of t which are less than a, the value of this function ku of t minus a will be 0, and for all the values greater than a, it will be k. And this is how you can represent that function, right? Again, assuming the value of the a, the switching time, to be some positive after time t is equal to 0. In that case, if your switching is happening at t is equal to a, your function will just get moved towards right here on the time axis. And why? Again, because your switching operation is happening at this time. And of course, after this time, when t is greater than a, right? So this is a. If t is greater than a, your answer will be k. And when t is less than a, right, all the way here to all the way here, the answer will be 0. So this is how we can model switching operation at some other time as well, right? We kind of talked about this. If a is greater than 0, the step is going to occur to the right of the origin. If a is less than 0, that step is going to occur to the left of the origin, right? So in case a is less than 0, then your function would have looked like something like this, right? Essentially, you are moving the original function ku of t with respect to a in time. So it's essentially time shifted function. And again, this is what we talked about. The value of the function is 0 when the argument t minus a is negative, right? Which is over here. That when your values are less than a, since your switching operation happens at a, so for all the values before the switching operation happen, your step function is exactly equals to 0, which means that argument t minus a is going to be come out to be negative again because t is less than a. This is going to be negative, and the answer is 0. When your t is greater than a, this argument t minus a is going to become positive, and the value is going to come out to be capital K, right? So this is what it means. Now I'm going to try and draw the function, another kind of interesting function. Essentially, I'm playing around with a step function here. And you must have done that in some basic circuit analysis course, some basic signal processing course as well. Again, I want to define another function where the value of the a is greater than 0, but the function looks like k times, again, k is just an amplitude, right? If this would be 1, we can just replace the value of the k with 1. And my function is u of a minus t, right? Initially, we had t minus a, or now we have a minus t, right? So I'm going to start with considering the same function k of u of t to be the original function as we discussed in the previous slide, which was starting exactly at, it was 0 like this, and then this, a jump at 0, t is equal to 0, and then goes all the way to k, right? So this was k, this was 0, and this was time. This was k of u of t. So assuming this function, right, I want to get to what this function looks like, k u of a minus t, right? The very first thing that I'm going to do is I'm going to time reverse it. What would the time reverse function is going to look like? The time reverse function is going to look like practically like this, right? So this is your t, this is your k. So this will be k times u of minus t. This is minus and this is t. Right? So this is a time reverse function. Again, the step is still happening at t is equal to 0. Now you can time shift this ku of minus t function as well, and then you can time shift it by a. For a, the values of a greater than a, you can time shift by a. If you're going to time shift this function, this step is going to move at some point a, right? And then the step is going to move a, and then this is the function that you're going to get practically, right? Which is modeled over here. So again, for this values of the k, for the values of t is less than a, the value comes out to be equals to k. For t is greater than a, the value comes out to be 0. Again, we got this function first by time reversing the original function, and then by shifting the time function by a, and a is greater than 0. So we are kind of did the right time shift and got this function. So essentially, yeah, these are basic signal operations, if you will, or functional operations that you must have learned in some in basic signal processing course as well. Anyhow, moving forward, right, this is a step function. Now we're going to look at a slightly more utility of a step function and how this is useful in terms of defining more signal operations. Okay, another interesting thing that we can do with the step function is we can use the step functions to create finite pulse widths, right? So for example, can I create some sort of this function using a step functions? And the answer to this question is, of course, yes. That was the whole point of this sentence, right? So we can use the two step functions, or sometimes, more, in this case, two, to define a finite pulse width, right? So for example, now assume that you have two step functions, right? So one step function is k times u of t minus 1, which is time shifted by 1, right? So it is starting at 1, 0, and k, right? It was 0 all the way, and then it was 1 all the way. And then you have another function, k t, which is starting at 3, right? And it was 0 all the way, and then it is starting at 3. Okay. So based on these two functions, k of u t minus 1 and k of u 2 t minus 3, if you were to subtract these two functions, right, what is the function you're going to get? the function you are going to get would be exactly the same pulse width. The pulse width is going to start at 1 and is going to finish at 3. 1 and 3. And other than 1 and 3, and the value over here is going to be k, f of t, and time, right? So this is how we can kind of define the finite pulse width functions as well. We can do simple algebraic operations of the step functions, right? So this step function, again, is this was at 1, this was at 3. We were subtracting both of them, and we are defining this kind of a finite pulse width operations, right? So there's another way to look at this beautiful analysis, right? So understand that, for example, in this particular case, if this were to be your function, u of t minus 1 is some sort of turning on a switch for a function k, and starting that is kind of turning on that function with a constant value of k, right, at time t is equal to 1. And then your second function, u of t minus 3, right, and inverse of that, if you are saying that you are adding the two, or if you are subtracting the two, then of course minus u of t minus 3. Right, and exactly at time t is equal to 3, right, you are saying that, okay, it's time to stop this function. So you can turn off and turn on a signal using step functions. That's the bottom line. And we're going to do an example to make it more understandable in a second. Right, so we can potentially use step functions to turn on and turn off the linear functions I derived. So let's do an examples to see what exactly I meant by that. Okay, so this is interesting. This is a function over here, and this function is called as a piecewise linear function. Why a piecewise linear function? Because it is only linear in some pieces, right? It is linear over here, it is linear in this piece, and then it is linear in this piece. Otherwise, it is made of different line segments. So it's called a piecewise linear function. So what I'm going to do is let's model this function. Can I write a time domain function of kind of a piecewise linear approximation? Can I write some sort of an equations for that and define the linear pieces separately? So let's do this. F of t should be equals to, right? We know that f of t is 0. The value is 0 for t is less or equals to 0. Okay, great. At 0, we have a linear segment, right? You can define any linear segments by this equation, mx plus c, right? Where m is the slope. Of course, this is x-axis variable. In this case, it is going to be t, and c is the intercept. Okay, using this equation, you can define any of the linear functions. Okay, now let's look at that. The intercept over here is 0 because it is starting at 0. And what is the slope? Slope is delta y over delta x. The delta y over here is 2. Delta x is 1. So 2 over 1 is 2. So I can easily write an equation over here, which is 2 times t plus 0, because the intercept was 0. Now this is from 0 to 1, right? From 0 to 1. And 1 second. Now, okay, good. Now I'm interested in defining what this linear equation is. Again, this is also a linear equation, so I can write an equation for this by finding an intercept and a slope. Okay, let's start with the slope. The slope is, right, so this is 3 and this is 1. So delta x is over here and delta y is there, right? So delta x is 2 and delta y is 4. 4 over 2 is, again, 2. And the slope, as I can see, is going down, so it's a negative slope, minus 2t. And what is the intercept? I can, right, so moving from 1 to 2, it has the same slope, right? Moving from 1 to 2, it goes 2 in the y-axis. Sorry, so it is gonna cross this y-axis at 4, right? Because it is gonna move another 2 steps up. So you get minus 2t plus 4. And again, this is in between 1 second to 3 seconds. Now let's define this function, right? Again, this has an intercept of all the way over here, right? Since the slope of this line is the same and the slope is positive, right? A rising slope, so you can call it as 2t. What is the intercept? Intercept should be, right? So this is -2. It gets to -4 here, -6 here, and is going to hit the y-axis at -8. So it should be -8. And this is in between 3 seconds to 4 seconds. And the final is again 0 for time greater or equals to 4 seconds. Beautiful, right? So we ended up defining the function f of t into these different times. Now, what we are going to do is, now we are going to use step function to turn on and turn off these pieces of function. And we are going to define a kind of a one uniform function. Okay, so for example, I can see that this 2t, right? So I plus 2t, I can turn on at time t is equal to 0 and turn off at time t is equal to 1. Next, -2t plus 4, I can turn on at 1, t is equal to 1. I can turn off at t is equal to 3. Next function, 2t minus 8. 2t minus 8. I can turn on at t is equal to 3. I can turn off at t is equal to 4. And then you have 0, right? So I can practically write my function down, which I'm going to do in the next slide, by using the step functions, right? Okay. So let's do that. I'm going to start with 2t. So 2t was being turned on at 0 and being turned off at 1, right? So my f of t is going to come out to be, I'm going to write 2t, and then it is in between 0 and 1, finite pulse width, right? So u of t minus u of t minus 1. Right? It was turned on here and turned off at 1. Next, -2t plus 4, right? Minus, what is happening to this? -2t, sorry about that. -2t plus 4. Let's call this so I can, okay? And this can be turned on at 1 and 3. 1 and 3, right? So you can turn it on at 1 and turn it off at 3. Again, this is on and this is off. And then again, you can add another plus. What is the function? 2t minus 8, 3 and 4. 2t minus 8, 3 and 4. So u of t minus 3 minus u of t minus 4. You can turn it on at 3, turn it off at 4. So this is a function which is valid for all values of t, right? So this is valid for all values of t. And you don't need to define it as kind of a piecewise function like you were defining it over here. So step function, we can play around with the step function and do a lot of interesting stuff. Okay, this is, by the way, how you can represent it, right? This is your equation 2t, which was kind of turned on here and then turned off. If it would not have been turned off, it would have continued to go on like this. Then you ended up turning on this signal, and this signal was turned on here and then turned off here, right? So these are these extra protrusions that you can take it out. And after that, you turned on this signature at this point and turned off this signature at this point, right? So all of this are these extra kind of protrusions of that, which are not relevant. Sounds good. So practically, again, in this part of the lecture, we're going to kind of end the step function part of it. right? So in this part of the lecture, we talk a little bit more about the step function, where we were interested in looking at our switching function can happen at any other time. It can happen at t is equal to a as well. So you can just kind of time shift it. And then we can also look at how we can use a step functions to turn on and off signals as well. And we converted this kind of a piecewise linear function into kind of a one linear form which is valued for all values of t by using the step function applications. Okay, so in the next part of the lecture, we're going to focus on the impulse function. So I will talk to you in the next lecture. All right, thank you. Bye bye. Have a good day.